So it's my great pleasure to have Carl Varva today from the Lund University, who is working under the supervision of regionality on depth of experimentation and Bayesian optimization. And we have the great pleasure that he's going to present his ICML accepted work, vanilla Bayesian optimization performs great at high dimensions. So we're really excited for your talk, and the stage is yours.
Thank you, and thanks for having me. It's super exciting to get the opportunity to talk about this. Yes, so this work is joint work with Erik Hellsten, who was a postdoc in our lab, and as you mentioned, my supervisor, Luigi Nardi. So, the purpose of the talk today is as I've understood it, people are at least know of Bayesian optimization, so I'll give a relatively brief outline on what it actually is and why it has a spot in the AutoML seminar series. And for the second part, there will be a lot of build up to the actual method itself, so we'll understand how the difficulty of a Bayesian optimization problem is determined, develop into the assumptions that are really key to this work related to difficulty, and then demonstrate why a change in the fundamental assumptions related to Bayesian optimization end up solving a lot, especially in the context of high dimensional optimization. So we'll get going with explaining BO itself. Uh, so the problem at hand is the optimization of a complex black box system through iterative pointwise queries, a systematic trial and error, if you will. The system is expensive, so it cannot be exhaustively evaluated. And moreover, the system is typically noisy, so repeated queries may yield different results. The very seminal example of this is in hyperparameter optimization of neural networks or other machine learning algorithms, where you want to find some optimal or best possible accuracy in a finite amount of time, and you want to change the learning rate, scheduling, the weight decay, the batch size, all possible choices related to a neural network in terms of the hyperparameters. There's some background noise in someone here. I'm not sure if I'm the only one who picks it up.
Yeah, I just muted it. Go ahead.
Okay, thank you. Right. So the formal problem definition of this HBO problem, if you will, is to find some optimal X star over a search space, typically RD, of a function f of X, where the objective function here is indeed the neural network F. X is our parameters to optimize, the learning rate, the L2 norm, what have you. And after having observed a bunch of queries, we have some hopefully almost optimal set of parameters, the best learning rate, the best L2 norm. So expensive to evaluate, only observed through pointwise queries, and it may be noisy. Hyperparameter optimization is a typical example, but we may also have other applications, such as robotics, where we can tune all types of rotational velocities, starting coordinates, basically any sort of degree of freedom that you have in a robot, which basically increases the dimensionality of the problem pretty quickly. Right. And so then we get into Bayesian optimization itself. What does it do? Well, we have some objective function f here in black that we do not observe. We only observe the green dots, which are sort of indication of what the function will look like. And to model this, we employ a surrogate model, typically a Gaussian process, which smoothly interpolates between or roughly in the points. Doesn't have to be if the problem is noisy. So we learn the surrogate model, we choose a next point through some measure of utility that appreciates either a high function value or a large degree of uncertainty. So here we have EI, expected improvement, which chooses the point based on how much it will, in expectation, improve upon the current incumbent. And that leads us to choose over here, a relatively exploitative query. Now we're no longer curious what happens over here, and rather we want to go over here where we basically have no idea. So it's a completely exploratory query. And then we, once again, choose a query that we believe to be good based on this criterion, and we repeat until we're typically out of budget or until some sort of convergence criterion. And so that is BO in a nutshell. We build a surrogate model that interpolates the problem, and then we choose based on some measure of utility. Right. So while that hopefully looks relatively simple, the idea of it, there is a common sentiment in the Bayesian optimization community that this doesn't necessarily scale to higher dimensional problems. So when you add more parameters that you want to tune, this type of surrogate model basically breaks down. And as a matter of fact, this is basically a well-established fact in the BO community that vanilla Bayesian optimization does not scale beyond d equals either 10, which a lot of people say, or 20, or 30, or just some moderate number of dimensions. But most people agree that this is true. However, we make a radically opposite claim and say that vanilla Bayesian optimization actually performs great in this setting. And this, hence to the work that I'm going to present now, which resulted in a publication at ISML, that the vanilla algorithm indeed performs great. It's just a matter of which assumptions you make on the surrogate model. And so that leads us into the paper, the second part of the talk, which is basically to explain why this is. So the second part outline is to first understand how the difficulty of a BO problem is assumed when you construct the Gaussian process. We'll delve into the assumptions and the difficulty that comes with it. Then we will tie that to the dimensionality of the problem and demonstrate that as you increase the dimensions of your problem, the problem difficulty will exponentially increase. And then we will show why this slight change in assumptions basically tunes the problem to have a sensible assumed difficulty, even in very high dimensions. Right. In order to do that, we're going to take a step back and look a bit more carefully at the Gaussian process. So a Gaussian process is, as many of you may know, a distribution over functions, which is represented through some typically constant or zero mean, and some covariance function, which measures the similarity between points, either observed or unobserved. So this function here is a squared exponential kernel, which, while I'm not going to go into it in detail, says that points that are nearby one another will likely have very similar values. So under this measure of similarity, a function may look like this, where it's very smooth, meaning that points that are nearby are likely to have high values. Another function that could come from this very same kernel specification is this one or this one. And if we do that a million times over, we basically get this, the Gaussian process itself, for which we can compute the mean function and the covariance function in closed form. But what exactly says that our GP should look like this? Say, if we were to toy with this parameter here, which may not have been obvious from the last slide, which governs the smoothness that we expect to see, we get something that looks completely different. We get something that's wigglier and less smooth. So then it may look like this, or this, or this. And notably, these functions, which if I were to do this over and over, gives us this Gaussian process, suggests that our underlying problem is much more difficult to optimize. Notably, any of these three are way more complex than any of these three. So what exactly is it that determines which type of smoothness we should have in our model? We'll get to that in a bit, but first we'll connect this type of observation to what exactly constitutes difficulty in a BO problem. So, what is the practical meaning of difficult here? From the previous slide, we constructed a GP that was rather smooth and one that was not at all very smooth. And to represent difficulty here, we're going to be very concrete and say that difficulty measures approximately how many independent points can I obtain with my current model. So with this model to the very left, there are no more independent points to be had. There is very little uncertainty left in the GP. And so if I were to add another point here, it would be highly correlated to the ones I already have. And this one right here, we can probably fit about 1 or 2 more points in that are roughly independent of the rest, but barely. Whereas in this one, we can fit a lot more points that are of maximal uncertainty and will be almost uncorrelated with the current data, meaning that the addition of those points, basically the points we already have, doesn't give us any information about this new point, say right here. And this can be measured, this notion of information and the maximal information we can fit in a GP, where more information is bad because it means we can fit more points that are uninformative. So if we have this length scale in green, we're basically already done. We're currently right here where we have 5 points and we're already saturated in terms of the points we can fit. Whereas with this blue one, we can fit a few more, but then the information gain starts to decrease a lot more. Whereas with the red, we don't deviate from this line where we can constantly add more points and are still not saturated a lot later at approximately 20 points. So that is to say that we can basically fit 20 points that are almost independent in this GP, which means that inference becomes quite meaningless. And this is measured, as in this plot, by the maximal information gain, which there is lots of theory in seminal work. This one that won best paper in ISML 2010. So that hopefully creates some intuition on what difficulty actually means. It means roughly how many points can we fit that are almost independent of one another. Right. So now we ask, when is Bayesian optimization unsuccessful? Well, as I said before, this GP right here requires basically 5 times more iterations to solve than this one right here, if this model is correct, and if this model is correct. But in practice, we don't really know whether we should go with this one or this one or this one. It would be very convenient if our problem looked like this, because it would make it very easy. But that's no guarantee. And that's something we have to infer from the data. And so how do you do that? Well, we need to determine the hyperparameters of the GP itself. And that is typically done by estimating and maximizing the marginal likelihood through MLE, which we do by this formula, which is basically to maximize the probability of the current data that we have plus minus some regularization term. So that we want the simplest possible solution that explains our data. And that would typically give us this in this specific scenario. But what one typically does in settings where you don't have a lot of data, where you are budget constrained or where you are in high dimensions, this problem is typically over-parameterized. So the maximization will be ill-posed. And to counteract this and to encode the beliefs that you as a user have on the problem at hand is to add a prior on the hyperparameters. Basically something that says, I expect the problem to be roughly this smooth or to have some certain level of noise, which would typically come in roughly this form, where I say that my length scales, this parameter that we saw on the kernel, on the GP kernel previously, follows some sort of distribution. Here, as an example, I have a log normal distribution where we effectively say that, well, the mode of this distribution gives us roughly this GP, but this could likely be an explanation as well. So what is the connection between length scales and high dimensional BO? Well, we saw previously that the length scale itself has a drastic impact on the complexity of the problem. But what happens then when we go beyond this one-dimensional setting that I showed previously and instead plot what happens when the dimensionality increases? How many more points that are roughly independent can we fit by adding another dimension? Well, for a fixed length scale, we can add exponentially more such points because points have to be close in all dimensions in order for the GP to perform meaningful inference. And so the MIG escalates quickly with the dimensionality. We don't run out of high variance points. And so that's where we see in the left here, where in dashed, we have a kernel that is completely independent. No point observation that we have provides any information about any other. And for 2 dimensions, we quickly saturate here and observations start becoming highly dependent. Whereas even for d equals 18, we practically require 2,000 or 3,000 points in order to have meaningful correlation in our model. And if we don't have meaningful correlation, how can we then expect to perform efficient optimization? We really can't. So the statement that 10 or 20 or 30 dimensions is where vanilla BO stops working is sort of true, because you can see here that, well, we need thousands of observations even to make a 18-dimensional problem work under a conventional prior, that is. And so through this prior on our length scales that say that we expect every dimension to look roughly like this, that every dimension has some action going on that requires substantial effort in order to optimize, we assume that each dimension is important. So each dimension of our problem is meaningful for optimization, which effectively yields a curse of dimensionality. So this prior that we impose on the length scales, which says that each dimension matters, is that a correct assumption? Well, we don't know. All dimensions of our problem may matter, but with this assumption, we are basically assuming the curse of dimensionality, and we're assuming that our problem is impossible to solve if we have a sufficient number of dimensions. So if we assume that all dimensions matter, 18 dimensions is not a feasible problem to optimize. So then, like, why does high dimensional BO exist at all? By now, we should have established that you cannot assume that everything matters if you have a sufficiently high number of dimensions. And most dimensions that work in this, most methods that work in the high dimensional setting don't assume that all dimensions matter. As a matter of fact, the most common work in high dimensional BO is to assume a low effective dimensionality, meaning that very few dimensions actually matter, like this very seminal work in random embeddings, where we assume that this dimension x1 carries all the action of this problem at hand, whereas if you traverse x2, nothing happens. And by randomly slicing through this space and optimizing on that slice, you should be able to optimize the true problem. Another conventional assumption is that we have additive decomposability in our objective, meaning that we can optimize small, lower dimensional additive components in order to decrease the total dimensionality. So both of these very conventional approaches drastically bring down the effective dimensionality of the problem, ergo bringing down the complexity of the problem by substantially restricting the assumptions that are placed on the model. As you can imagine, this specific approach is rather restrictive because your problem should hopefully adhere to this specific structure. There are other related works on this as well, but I'm going to skip them for the purposes of this talk. Right. And so having established how complexity and dimensionality link together and how other approaches address complexity and bring complexity down through various assumptions, we now get to our method. And it's sort of a blink and you'll miss it type of thing because it's very subtle. So now we just want to assume our way out of the curse of dimensionality. We are assumed our way into it by saying that all dimensions matter in conventional BO. But what if all dimensions kind of matter? So we don't truly know the length scales of the problem. We don't truly know how smooth each and every dimension is. But we can go at the problem from the other end of saying the problem, regardless of the dimensionality, has a sensible level of difficulty, and we will adjust our length scales to cope with that difficulty. So it's a well-established fact that the distance between random points increase as the square root of d as we increase the dimensionality. So by adding one more dimension to our hypercube and sampling randomly, the distance between those points will increase by the square root of d. Which means that as this box increases in size, we can scale down the absolute volume of the box by scaling the length scale prior accordingly. Which means that we make this modification, saying that our length scales come from a distribution which scales with the square root of d. So as we increase the dimensionality, the relative distance that we traverse in each dimension decreases by square root of d. And this is truly all there is to our method. We are saying that each dimension matters a factor of square root of d less as the number of dimensions increase. So this change actually negates the assumed difficulty increase up to small log factors, which basically says that we are assuming that the difficulty of the problem stays constant as we increase the dimensionality. So in practice, it looks like this. For d equals 1, we can afford to optimize a function that looks like this. It's highly complex, but it's only one-dimensional, so it's simple. If d equals 10, well, the length scales are assumed to be much smoother. You can see that functions are now much simpler, and their per dimension are much simpler to optimize. If we go up to d equals 100, we're almost at the point of linear regression in each dimension. So all dimensions have to be highly smooth in order to successfully optimize this problem. Crucially, we can still find evidence that certain dimensions matter more than others if our MLE map estimation successfully infers it. So this is not a set in stone type of thing, but this is what we assume a priori is the case. Right. And so that we then benchmark our method on how difficult do we assume the problem to be relative to these other methods that assume a low effective dimensionality or additive decomposability. Well, we see that if you just gather 1,000 data points and ask, do we have meaningful correlation in the GP, where anything below this line means that we do have meaningful correlation. We see, as we saw previously, that the typical global GP here in pink basically stops having meaningful correlation in the GP at 20 dimensions. Local approaches like Turbo do much better because they operate in a smaller space. And at a dimension of 250, it stops having meaningful correlation in the GP. Random embeddings, naturally, since they slice through the space and optimize in, here it's a 4-dimensional space, have the lowest complexity by far, but its assumption is very restrictive. Whereas our method here in blue has meaningful correlation, and by a good margin, for any dimensionality. Basically, it flat lines right about here. And so now we're at the point where adding more dimensions really doesn't matter for the complexity, the assumed complexity of our method. Right. And that brings us to the results. Note that we have only assumed, nothing else, that our problem is simpler as we increase the dimensionality, that each dimension matters less. And so how does this go? Well, firstly, we benchmark on synthetic tasks where our algorithm here in blue is benchmarked against basically all of the combined state-of-the-art across various structural assumptions for high-dimensional Bayesian optimization. So we call our method here D-scaled P of L, dimension-scaled length-scale prior, and benchmark on a bunch of tasks that are low effective dimensionality, and then we add a bunch of meaningless dimensions. So Levy here is a 4-dimensional optimization problem where we have concatenated 21 dead dimensions in the end, but the optimizer crucially doesn't know that. And so our method here in blue does very well, especially as we increase the dimensionality from 25 to 100 to 300 to 1,000. It's perfectly capable of optimizing the problem regardless of the dimensionality. Whereas other competing methods like bounds and SASPO in pink and brown assume a low effective subspace, the exact assumption that these synthetic problems have. So while we do not assume the specific structure of the problem, we're still competitive with the very best in the setting. I skipped one slide intentionally, and I'll get back to it in a while. We then benchmark on a broad collection of high-dimensional optimization tasks from 124 to 6,400 dimensions. These are all real-world tasks. So MOBTA is a vehicle design problem. Lasso DNA is tuning a lasso model in 180 dimensions. There's an SVM hyperparameter tuning problem, and the last two are tuning linear policies of reinforcement learning tasks. So we see that for all problems, but effectively two, we are the best performing method, occasionally by a very good margin. And notably, we also run substantially faster than SASPO and Brown, that is the competing method on many of these tasks. And, well, related to the D equals 10 or 20 or 30 questions, clearly vanilla Bayesian optimization, tuned the right way, can optimize a 6,400 dimensional problem, which is basically something that has, to the best of my knowledge, never even been attempted before. I should also note that here on ANT, bounds, the second best method, gets a very strong initialization. So this dashed line is where the DOE phase of bounds ends. And so it basically has a very good starting point, which no other algorithm really has. And since this is supposed to be vanilla BO, it should also be able to handle the low and mid-dimensional setting, where we benchmark against conventional map estimation, where we say that all dimensions matter, and against Turbo, that is sort of meant to work across any dimensionality, any scaling, what have you. And we see that, well, in a very low dimensional setting, we're basically back to truly standard BO without any assumptions. And so then it should really just be competitive. But as we go to d equals 12 to 14 to 16 to 32, our method just holds up where map estimation just falls off the face of the earth. And turbo, as we saw previously, should scale up until d equals roughly 250. And that is also what happens here, where turbo for these problems are sometimes competitive, but as we go substantially above 250, it drastically falls off. So our method holds up across dimensionalities, whereas other at some point fall off, all through this assumption on the difficulty of the problem. And so more specifically, and this is the last slide, why does our method do well? Well, our prior tries to get the basics of Bayesian optimization right. The first one is meaningful inference. If you have a sensibly calibrated prior that allows you to infer which points are good. And so in conventional map, this is a 180 dimensional problem. By assuming that all length scales matter, that all dimensions matter, you quickly lose all correlation in your GP. You quickly revert back to the prior. So as you can see here, for the predicted value and the actual value of the function sampled randomly in the search space, we infer absolutely nothing. And that is exactly in line with our assumption, because you need so much data in order to say anything at all. Whereas our method, while not perfect, has a very an okay idea of what's going on in the function at hand. And when you have 180 dimensions, that is arguably all you can expect. You cannot predict with a great degree of certainty what values you are going to see if you have a couple of hundred points in a couple of hundred dimensions. So we see that it's calibrated, not perfect, but calibrated. Secondly, there's an actual exploitation trade-off, like we saw in the beginning. If the model is misinformed, the algorithm will only exploit. And this I emphasize a lot. It's exploit, not explore. The proof of this is in the paper, where we actually prove that if a BO algorithm has no idea, if there is no correlation in the data, it will basically only go close to the current best point. And we benchmark that too, where we see that our method here in blue against conventional map in either yellow or red actually keeps a relatively modest average distance to the current best point. Whereas these other methods here, once again, measured as the distance from the current best point to the subsequent query, it stays extremely close to what it currently believes is best through the entire optimization. So standard BO, meaning with conventional map estimation, stays exceedingly local if it's not calibrated right. And thirdly, our method sometimes actually identifies the right dimensions. Not often, not always, but kind of often. So this is the 388 dimensional SVM problem demonstrated here, where our method does pretty well. And we see that that problem is known to have 3 very important dimensions, and the rest don't really matter. And here, ranking all 388, these are the most important 12 dimensions. These are the ones that are known to matter. And so we get 2 out of those 3 exactly right. That this dimension and this dimension should have the lowest length scale values. And that is also what we observe. Now, it's not perfect, meaning that a good amount of the times in these box plots, it actually fails to identify these. Yet the algorithm still works because it is just better calibrated than the alternative. So what are the conclusions here? Well, firstly, the vanilla BO algorithm, if tuned right, is intrinsically not ill-suited to higher dimensional problems. It works, you just have to assume sensible things. And secondly, model level are vital to the success of any BO algorithm for any dimensionality, because you need meaningful correlation in the GP in order to facilitate successful optimization. And that is it. Thank you for letting me present, and I'm happy to address any questions and any feedback you may have afterwards. I am happy to take it either in Zoom chat, through email, whatever. Thanks.